Hello, ladies and gentlemen. Today we're going to be talking about arcs, angles, and inscribed angles in circles. So what you're going to need is your notebook and a foldable that you should have gotten from me, a pen or a pencil, and maybe a calculator. The math shouldn't be too hard today, but a calculator may help you. Okay, so for this first part, we have a couple definitions that we should be getting down. So we have 5 major definitions for this circle unit. The central angle, the arc, minor arc, major arc, and semicircle. So a central angle is an angle whose vertex is the center of the circle. So in my picture below here, my center is C, and so a central angle is like this angle, angle ACB, or there's another one. It could be angle DCA, that's another central angle, and even this big one could be a central angle, okay? Okay, an arc is a piece of a circle that is named with 2 or 3 letters and measured in degrees. So when we talk about arcs, like arc AB, this would be actually a minor arc. Arc AB, or minor arcs, are always named with only 2 letters. So it's a part of a circle that measures less than 180 degrees. I'm going to use purple for a major arc. So a major arc then is a part of a circle that measures between 180 and 360, and it's named by 3 letters. So if we look at our picture below, like from A to D to B, that would be one major arc because it's more than 180 degrees. And of course, a semicircle. Oh, sorry, I should probably label. So our major arc would be labeled a DB. That's our major arc. And then a semicircle is an arc whose endpoints are the endpoints of the diameter of the circle, which makes sense, right? So DB. So that is my semicircle, is that arc. Or we could be going this way from D to B, okay? Or basically we always know that a semicircle is half of a circle. Okay, more things that we should know, or more definitions that we know. When we measure arcs, when we measure a minor arc, we measure it based on its central angle, and when we measure a major arc, we take 360 minus the minor arc, or we can also think of it as measuring that big central angle that's larger than 180 degrees. So let's look at these examples. So the measure of arc AB. Well, if we look back at its central angle, it's 50 degrees, so that means that the measure of my arc would also be 50 degrees. And then if we look at the measure of angle, or the arc BC, that goes back to the central angle, which is 130 degrees. And if we look at our major arc, the measure of A to E to C, well, that's a semicircle, so I know that it's going to measure 180 degrees. And if we measure the major arc B to C to A, so if we're measuring this big piece, it's going to be 360 minus that 50, which would be 310 degrees.
So before we do some examples or any theorems or anything, let's obviously start with some vocab or some definitions. So an inscribed angle is an angle whose vertex is on the circle and whose sides contain chords of the circle. So in our picture, our inscribed angle would be the angle BCD, or this angle right here. So notice that its vertex C is on the circle and its sides or segments CB and CD are chords of the circle. Another term that we need to know is the intercepted arc, or the arc that lies in the interior of the inscribed angle and has its endpoints on the angle. So the intercepted arc of the inscribed angle would be arc BD. So when we say the interior of the angle, this is the interior of the angle, and the arc lies between the points B and D, which are the endpoints of that angle. And so I just want to make sure that we know what I'm talking about when we say inscribed angle and intercepted arc before we do some problem solving with in circles. Okay, so the theorem that we want to talk about knowing inscribed angles and intercepted arcs is that there's a theorem for the measure of an inscribed angle. If an angle is inscribed in a circle, then its measure is half the measure of its intercepted arc. So given the circle BAC, where the angle BAC is the inscribed angle and the intercepted arc is BC, we're saying the measure of angle BAC, or the measure of this angle, is going to be equal to half the measure of the arc BC in degrees. So that's an important theorem that we need to know. So make sure you get this and the picture written down in your notes, because if we just wrote this down, but we don't have a picture to reference it to, you might look back in your notes and be like, what the heck did I mean when I wrote M angle BAC is equal to half M arc BC? Okay, so now we're going to use that equation where the angle is equal to 1/2 the measure of the arc. So in number 1, they gave me the inscribed angle. So angle ABD is 90 degrees, but we need to find the measure of the arc AE to D. And it's pretty obvious that it's a semicircle, right? Because we know that AD is the diameter. So we know that this has to be 180 degrees. But if we were to use the equation, we would need the measure of the angle, which is 90, is going to be equal to 1/2 the measure of the arc. And in this case, let's say we didn't know it was a semicircle, then we would have had to set up an equation like this, multiply both sides by 2 to solve for x, and we get 180 is equal to x. But this one was a little easier because we know already that a semicircle measures 180 degrees. So therefore, the measure of arc AED is 180 degrees. Okay, now moving on to number 2. They now gave me the arc's measure in degrees, but we need to find the inscribed angle's measure. So now we have x for the angle is equal to 1/2 times the arc's degree, which is from A to D, is 196 degrees. So x is going to be equal to 98 degrees. So the measure of angle ABD, or the inscribed angle, is 98 degrees here. 98 degrees. And that is my answer for number 2. So just remember that it's the angle is equal to 1/2 the measure of the arc. So that's the theorem that we want to remember. Okay, another important theorem that we need to know is that if two inscribed angles of a circle intercept the same arc, then those two angles are also congruent. So in my picture, the angle XWZ, or this angle right here, and the angle XYZ, or this angle right here, they are intercepting that same arc from X to Z in the circle. So this intercepted arc is the same for both of those inscribed angles. So therefore, we're saying that those two angles, W and Y, are going to be congruent. So that's a little simple, easy theorem. That's sometimes hard to remember because you just forget, but it's good to know. Okay, so some more definitions. Again, these are all formal definitions in this unit, and for the most part, they're pretty self-explanatory, but just in case you were to ever hear these words or see these definitions in standardized tests, you know what they're talking about. Okay, so an inscribed polygon, or when something is inscribed, it's within the circle. So an inscribed polygon is a polygon with vertices all on the circle, but it's inside. So it's always inside the circle, and its points, or whatever we're talking about, if we're talking about an inscribed angle, then its vertex is always lying on the circumference of the circle or the edge of the circle. When we say circumscribed circle, that means that that shape or that circle is around the inside, so it's on the outside. So when it's circ or CIRC, that means around outside. So just so we know the difference between inscribed and circumscribed, because those words are definitely hard to interchange. So inside of a circle or circumscribed is around the outside. All right, some more important theorems. So if a right triangle is inscribed a circle, then the hypotenuse is always the diameter of the circle. If one side of an inscribed triangle is the diameter of the circle, then the triangle is a right triangle and the angle opposite the diameter is the right angle. So basically what we're saying is if you're given a right angle with the point on the inside touching the circumference of the circle, then its hypotenuse of that right triangle is the diameter. And if you've been given the diameter of the circle and a triangle inside, then we know that this angle opposite of the diameter is going to be 90 degrees. It works both ways. That's what these two theorems are trying to say. So let's look at some examples using those theorems. So if PQ, they're telling me, they didn't say in the directions, but given PQ is the diameter, then we know the angle across from it is 90 degrees. So in order to find x, we just say 90 is equal to 3x, divide both sides by 3, and voila, x is equal to 30 degrees, or 30. And we have one more important theorem. So we're just continuing these theorems in our notebook. A quadrilateral can be inscribed or inside of a circle if and only if its opposite angles are supplementary. Remember that when we say if and only if, it works both ways, just like an equation sign. So if opposite angles are supplementary in a circle, then there's probably a quadrilateral in that circle somewhere, inscribed in that circle somewhere. And if we have a quadrilateral already inscribed in a circle, we can assume that their opposite angles are supplementary. So angle A and angle C are opposite of each other, so those two things added together will give us 180. Angles B and angle D are opposite each other, so those two things added together equal 180. So let's look at some examples with that theorem. So now we have y plus 80 is equal to 180 because this and this are opposite of each other. If we add them together, that equals 180. So if we subtract 80 from both sides, we know that y is equal to 100. And if we set up the other one, x plus 85 is going to be equal to 180. So if we subtract 85 from both sides, 180 minus 85, x is going to be equal to 95.
That is all I have for you, ladies and gentlemen, so I want to thank you for taking good notes, and I shall see you soon.